Welcome to pre-calculus video for skill number 42. I can use intercepts, end behavior, and factoring to sketch graphs of polynomial functions. And featured here we have pack weight distribution for an internal frame pack and an external frame pack. You can see the frame right here. And what we have is three different colors representing medium or light or heavy weight. And the trivia question is, how should we load our backpacks? Do we put heavy weight at the top, or do we put light weight at the top, or maybe this middle area is where we pack all of the middle weight? Alright, so we're going to start here with problem number 2, which is just a small extension of our previous skill, and it's asking us to find the intercepts and then use that to sketch the function. So we're used to each factor telling us one of the intercepts, so we can see that there's x-intercepts, or in this case t-intercepts, at -2, 0, 3, 0, and -5, 0. Basically, those are the three spots where we're going to cross the axis. So at -2, at 3, and at -5. We can also find the c-intercept, or the y-intercept, by plugging in 0 into the function, and we'd get a y-intercept, or in this case c, at 0, 3 times 2 times -3 times 5. So 3 times 2 is 6, times 5 is 30, times 3 is 90, so at -90. So this will be -90. Which obviously, if we were counting by ones on the grid, we wouldn't be able to get to 90. So I'm going to count by 15. So this is -15, -30, -45, -60, -75, -90. Alright, so we have an intercept there. Now the last thing is we need to be able to pass through these 4 points, and we can see that our leading coefficient is positive for this third degree polynomial, which means it's generally going to move in that sort of pattern where it's got two turns, and so there's one turn, a second turn, and it's moving in a positive direction, so generally uphill, which means this function is going to pass through here, down here, and then up like that. And that's pretty much as accurate as I would need you to do the drawing. You can, if you wanted to, find extra points, like what's the height at a value of -4, to kind of figure out where that goes up to. But you've got the general shape and you've passed through the 4 points, so that's good enough for this problem. Alright, let's move to the next one. Problem 4. We can see that we have t-intercepts at this first spot calls for a t-intercept or an x-intercept at 0, 0. And then the next one gives us one at 3, 0. And then we have a double at -1, 0, or what you would say a multiplicity of 2. So that's what this 2 represents. To find the c-intercept, we're going to plug 0 in for t, and we'll get 2 times 0 times -3 times 1 squared, which is 0. So our c-intercept is at 0, 0. Which makes sense. If we have an x-intercept at 0, 0, then we'll have a y-intercept at 0, 0. So if I plot my x-intercepts at 0, 0, 3, 0, and -1, 0, and then I plot my c-intercept at 0, 0, this polynomial is of 1, 2, 3, 4 degrees. So it is, because it's 4 degrees, it's going to look something like this or that, or very close to that. And our leading coefficient is positive, so now I know it can't be this one. It's going to look more like this one. And so if those are my intercepts, maybe what I get is something going off and up like that, and then we've got to drop below, and then we come up like that. So that's not a perfectly clean drawing. If I erased it, maybe those 3 things can be done together in a cleaner fashion. There we have it, something to that effect. And again, we're just kind of trying to picture what the general shape of the polynomial is. We could, if we wished to, explore this further and find other y values or other c coordinates. Like if we plugged 1 into the equation, where would we be here? Or 2 into the equation, how far down would we be? Yeah, let's do that. Let's make a nice table of values. Let's plug in those values of -2, 1, and 2, just to see if we can create a more accurate drawing. So if those are our t's, then c of t is, this would be 20, this would be -16, and this would be -36. So if our grid is on a spacing of 1, then we'd be cleanly off the grid, but we'll say that, well, let's go by 5s. So 5, 10, 15, 20. So we now pass through that point, and then -5, -10, -15, so it's going to pass through this point, and 20, 25, 30, 35, somewhere down here. So our curve maybe looks a little bit more like this black curve. So you can see that with the use of a few additional points, we can create a far more accurate polynomial. And I use the calculator to find those values. You could actually even also graph the equation on your calculator to see approximately what it looks like. Alright, so here we have a problem which is not already factored for us. So we would want to factor this to be able to do this in a much easier fashion. I noticed that all 3 terms have a value of 4 in it, so I'm going to factor out a 4, and all 3 terms have t squared in it. So I'm going to pull out 4t squared, and I'm left with t squared plus 3t minus 10. And looking at that quadratic, I realized the quadratic can be factored to be 4t squared times t plus 5 times t minus 2. This tells me that I have a t-intercept at 0, 0, and it's a double or a multiplicity of 2. I have a t-intercept at -5, 0, and I have a t-intercept at 2, 0. So we'll draw those 3 points, 0, 0, 1, 2, 3, 4, -5, 0, and 2, 0. And for the sake of creating a nice graph, let's grab a couple extra points. Let's just figure out, where is it at? Let's go with 1, and we'll go with -1, and, I don't know, let's go with -4. So we can get some other values. So C of 1 is -24, C of -1 is -48, and C of -4 is -9,984. And I pulled all those things from my calculator. And obviously, that's going to be way off the grid, far down there, but I do know that I'm going to have something which is shaped generally like this. I have the double multiplicity right there, so that's this point. So in general, I'm probably going to get a curve which does something like that. I found the general shape again by recognizing that it's a 4th degree polynomial with a positive leading coefficient. So remembering my end behavior of polynomials. Speaking of end behavior, the problems 9 through 12 ask us to explain the long run behavior. So on problem 10, I'm going to count the degree. So I've got 2 terms, 3 terms, and 1 term. So if I were to distribute this all out, I would have t to the 6th. So this is a degree 6. So because I know it's a 6th degree with a positive leading coefficient, I'm going to go to my table, and I remember the table tells me that my end behavior is going to be like that. So as t goes to infinity, k of t also goes to infinity. So basically, as I move out here to the right, my function is also going to go up. As I go to the left, as I go to negative infinity, k of t is also going to go to negative infinity. And I guess using the arrows is maybe a little more accurate than equal symbols. Problem number 12, I'm going to count my degrees again. I've got 1t here, I've got 1t here, and I've got 3 of them here. So on problem 12, I have of degree 5, and I have a negative leading coefficient. So odd degrees point in opposite directions, and because it's a negative leading coefficient, it's generally moving downward. So, and again, remember, we can't really describe what's going on in the middle, but we can talk about end behavior. So my end behavior as we go to the right, so as t goes to infinity, k of t is going to go to negative infinity. So that's, as we go here to the right, we're going to go further down. And as we go to the left, as t goes to negative infinity, I guess we should say q of t. Q of t is going to go to positive infinity. So as we're going left, our function is increasing in that direction. So there we go, end behavior, revisiting that one. Finally, for problem number 14, we're asked to sketch a graph of the equation, which is basically what we were doing at the start. Our end behavior is we're of a degree 3 and a positive leading coefficient. So we're going to have something which probably does roughly that. We have a x-intercept of -4 and a double x-intercept at 1. If I stick 0 into the function, I'll get my y-intercept, and my y-intercept in this case is 4. So I need to draw this curve which passes through the 3 points. Knowing that this one is the double intercept, I can say that the function does something kind of like that, and it bounces off of it. So we get a curve which does generally something to that effect. And again, we don't know how high this goes or how steep the angle is, but we can plot that it goes through those 3 points. If we want to plot more points, then we would have to create a table. Okay, looking at problem 16, I've got a triple or a multiplicity of 3 at 3. So what that means is it's going to kind of flatten out right there at 3, either going up or going down. And then we've got a double at 2. So at 2 it's going to either drop down and hit, or it's going to come up and hit. So we'll draw those 2 key locations. And then finally, we should find the y-intercept. So in order to find the y-intercept, I plug 0 into the equation, which gives me -3 to the third times 2 squared, which is -27 times 4, and -27 times 4 is equal to -108. So if we count by tens going down, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, so way down there, we pass through a point right around -108. I notice that it is a positive leading coefficient, which means I need to start low. So I'm going to start down at the bottom of the graph. We're going to pass through this point. We have a double at 2, comes back down, and then we get something like that. And that's a really tricky graph to draw in that tight space. If we wanted to, we could have spread it out a little bit more, but the general idea is we're going to come up and touch 2, drop back down, and then as we come up to 3, we're going to have it flatten out, something like that. And the polynomial continues in that direction. Okay, problem number 18. 18 is a cubic, so it's a third degree, and you can see that because we've got one x term, second x term, and a third x term. We have x-intercepts at 0, -2, and +4. And if we stick 0 into the equation, we'd find that we have a y-intercept at 0. There's no multiplicity, so all these times we pass through it, and we see the negative leading coefficient. So in general, I've got end behavior that's going downward. So I start high. I'm going to pass through this point, through the second point, and then drop down. And we get a curve which looks approximately like that. Alright, thank you for watching the video, and the answer to the trivia question is the dark area is the heaviest weight. So on an internal frame pack, you kind of want to put that weight close to your back. The obvious thing is your sleeping bag usually goes down here in the bottom in this light area. Thanks for watching.